Hello and welcome back to another video. My name is abucnasty. Today we're delving into the world of fluids. We're getting into chemical science. So I've already got a design here that works completely fine in my mega base here, but I want to design, and I know some of these things are already overkill, and I want to get into trying to figure out how to optimize this and use less buildings that are here. For example, I already know that this system down here, even though this was just a standard blueprint that I already designed, this creates 240 red circuits per second. But we only require, effectively over here, like 185. So there's already like the potential to reduce and remove one of these machines here, and then that kind of same principle applies all the way down. One of the things that's going to drastically deviate from the previous videos that we've done is we've talked about everything, all the other sciences we've built so far have been made using upcycling of ore. So I've covered that in depth. Go look at the other videos that I've posted before if you're interested in that. So, and I've very intentionally chosen those three to be the first ones we talk about, because once you start getting into fluids and upcycling items made out of fluid, some of them are easy, but some are incredibly challenging. What do I mean by challenging? Well, the most challenging item that we have is sulfur. I've already done a bunch of research on this subject. Honestly, the calculator that I built to figure out the mining productivity, I've completely redesigned that calculator, and I've written over 2,000 lines of code in the last week to create a new simulator that I can use for basically calculating any type of quality upcycling recipe in the future. So I've invested some time into that. That's going to make my life significantly easier as we get into more complicated sciences. But it particularly helped with sulfur. So why did I spend so much time on sulfur alone? Like probably the 90% of this video is not going to be talking about sulfur, but was invested in figuring out a better sulfur recipe and upcycling method. So what do I mean by that? So sulfur is the hardest thing to get in any higher quality form, especially with minimal buildings. So it's convenient because you can make it in a cryogenic plant, so you can benefit from the 8 module slots that are in there. But the recipe itself is non-trivial. So because it's all fluid based, there isn't a quality fluid that we have, unfortunately. So in order to do that, and also all the byproducts that it creates, doesn't recycle back down into sulfur. So for that reason, upcycling it, even if you're using something like biosulfur, well, then you're going to have to make bioflux. Well, bioflux is also traditionally really difficult to make because the only way to make bioflux is through Yamako mash and jelly. So you could make it on Gleba and then send it back, but you also just need a very tiny amount of sulfur. And plus, with all my sciences, I'm wanting to design them on Novice so that I don't have the bot overhead and increase the throughput limits that are in the hub for shipping things over to the planet. So for that reason, I'm going, okay, well, we know that the sulfur recipe itself doesn't have anything that we can do other than asteroid like recycling in space. But I'm not wanting to add an extra ship. I'm effectively saying, like, if I'm going to go asteroid upcycling, then I'm just going to go straight to legendary. There's just no point in going and making it. But even in space, the recipe is not easy to go and create because you need carbon, and you're going to need basically carbonic asteroid chunks. And when you recycle them, or when you basically create it, you only have a 5% chance of getting back a carbonic asteroid. Whereas if you use the traditional method of creating carbon, well, that has a 20% chance to get it back. So effectively, you're upcycling and have like a 1 in 20 chance of getting back a carbonic asteroid chunk. So your odds are really low. And every time I've tried to make sulfur in space, it is a hard time to go and create it without a lot of buildings. So I've done math on trying to figure out the best form of sulfur recipe. So that's the first thing that I want to tackle. The rest of the items in this base are going to be pretty straightforward, except for the fact that we're using fluids now for making plastic. And plastic is really easy because, again, it is just straight petroleum and then just upcycling coal, which we've covered in previous videos. So this one is very easy to do. So I want to talk about sulfur first. We're going to go in a deep dive into that. I'll talk about some of the math that I did to figure out all the combinations. and it's relevant for it, so I'm not going to save that until the end. We're going to talk about that very first. So without further ado, let's get into the design, into the science behind it, and let's have a good time. I'll see you in the design lab. All right, so as opposed to other videos, I've already designed with multiple different versions of sulfur upcycling methods. So to start, what I'm going to show here is the first pass of doing this. You're going to notice some things that are a little bit odd. So like the fact that there are speed 2 modules being used in here and not speed 3s. And then also the same thing kind of having like a beacon distribution effect. And then as you get into later on, you're going to start noticing even weirder stuff that I have here. And like these are the final 2 designs. So there's speed 2s in both of these and speed 3s here. Speed 3s up here with efficiency, and then speed 1 with efficiency. Why did I choose all these things? So it turns out that there is an actual optimal solution for the amount of speed beacons that you can add, quality modules, and productivity modules. So intuitively, when you first start with this problem, you go, okay, cool, I've got a cryogenic plant. I'm going to throw 1 million quality modules in there because, yay, I get 49.6% quality. That means I get a 50% chance of getting uncommon. Well, this is only creating 6 per second. So this would create 3 per second on average, or a little bit less than that. So in order to supply the science that you actually wind up needing, we're going to need to be creating 30 per second. So that would mean that in order to actually do this, I would need, these would make 6, 12, that you get the idea. I would need 10 of these, right? So this is the number of buildings that I'm going to need to create to consistently make enough quality sulfur. And it's not good enough for me because I'd really ideally like to have 1 building. And the reason is because the UPS hog of doing this means that per blade, I'm gonna not need 10, I'm gonna need 20. Then multiply that by 8, and, well, you get the idea, right? So, effectively, at this point, 160 of these is way overkill in my mind for a science production on my main base. So what I'd like to do is cut this all the way down to when I started this off, I said, I'd like to have 4 of these. Well, how do you get things to go faster, right? Well, all right, we're gonna need efficiency module, or not efficiency. We need speed modules and we need beacons. Well, now the quality's gone down, but we're not making 68 of those. But, well, now it's 37% chance, so about a third of the time we're gonna get it. But that's already improved our odds, right? So that's better, but now we need to recycle the other products, which we already knew we would have to do, because we're gonna also get all the other different types and roll the dice on all the other quality, right? So then you would think, okay, so at what point, me continuing to add modules and speed beacons, is this going to get to a point where, okay, I'm making enough sulfur, so you see here, now I'm making 131, but there's a diminishing effect, right? If you can keep on throwing 1 million beacons on here, and this number will keep going up, but the quality goes down. So there is a point where it converges, where you're going to have the maximum amount of output for a single machine. And funny enough, I have the answer for you. I've done all the math and ran over 200,000 simulations to figure out what is, well, 200,000 simulations. I brute force calculated exactly the best optimal solution. So what do I mean by brute force calculated it? Well, earlier in the video I talked about that I redesigned my entire calculator. So I'm a developer, so I instead of going and doing everything in Excel, this is a way too complicated problem to actually do in Excel. So I've gone and created a entire system where I can go and now specify and build individual things. So I can now create modules, and I have all the different modules defined, their quality, speed, etc. And so I'm not going to bore you with all the code that I wrote, but GitHub is always linked below. If you're a developer or you like writing code or you're interested in looking at what I've done, for the developers in the room, this is using an entity component system model, which is very typically found in video game design. I've used that because we're modeling a video game, so it kind of makes sense. So this is now a way for me to very simply be able to define things like a cryogenic plant and calculate how much of the effects that a module and a beacon have. And I've tried to design it as close to the concepts that Woob already originally did, So like an effect is something that's in the game, that a module is an effect, a speed beacon is effect, and so forth, right? Productivity is an effect. So I wrote all this code, blah, great. What you're seeing here on the side, I ran all these simulations here to determine a couple things. So I'm just gonna go ahead and look directly into the results here so that we can talk about it. What I was going through and I was saying was, okay, so we zoom out a little bit and let's grab the header option. So what I wanted to know was, okay, given a combination of productivity modules, all the way to 8 items that could be there, all the way down to 7. So this is the number of modules in a cryogenic plant. So there's 1 in this case of productivity. And then over here, this is the number of modules that are quality based. And so what's really interesting is you're seeing there's a reason I'm using 1 and 7 in the designs that I just showed a second ago. So, and I also wanted to design this with, I want to minimize at the current production rate. I want to minimize the number of recyclers, so I chose that. I allowed it to choose, the algorithm to choose more than 1 recycler, but I wanted in the end, if it had the same output, to prefer a recycler. And then also I calculated here the number of recycler loops. Why? Because when I take 100, in this case here, I know that every single time this cryogenic plant is going to produce something, it's going to create as a byproduct 100 sulfur that is in the common quality. And I need the recycler to be able to destroy that amount. However, what's being chosen here is that this can destroy 104 items per second. But because it has its own quality, which is all the way over here on the right, the recycler is at 16% quality. So that means that some of it, or actually the majority of it, is still going to be common. So it's going to need at least 3 loops to completely destroy all of the input that is fed into it and produce some quality. And that's going to create, after those loops, a certain amount of uncommon. Now, granted, not as much as the cryogenic plant is putting out, but it actually makes enough that it makes a big difference. What do I mean by that? So here I've shown that how many recyclers, so the recycler itself, I gave it the option of just straight voiding the items as well by just putting speed modules directly in the recycler. So no quality at all, so just straight voiding. In that case, the best case that you're gonna get when speed is in the equation is all the way down here. It's the 200th best item. So, and just for the point of clarity here, there's a total of 246 items that were chosen. So it is one of the worst options to actually make this happen. So at every single point in here, and the best that you're going to get by just straight voiding it is, because again, you're throwing away, basically the recycler now is way faster, right? You can create 164 items. But now the cryogenic plant is slowed down because you're only relying on the cryo output, and that caps out at 17 per second that you're going to get. And then at that point, really, the only amount of output of Q2 is 12.56. So you need 3 of those cryogenic plants for 1 half belt of blue stacked blue science. But I know that I can get up to 32. So what this means here, and I know I'm going into the weeds, so please bear with me. We're going to get back to Factorio, but I want to stress this because I don't think anyone's done this yet, and I'm very proud of this calculator, so I'm just, you know, I'm geeking out here a little bit, so appreciate your patience. I'll have a timestamp if you just want to jump to the Factorio stuff, but anyway. So what's going on here is now we know our inputs of petroleum and water, and then this is basically telling us, and I've brute force computed all possible combinations of up to 4 different beacons and surrounding a cryogenic plant. And then I told it, hey, tell me how many speed modules in speed. I gave it the option of speed 1, speed 2, speed 3, all in legendary quality. I didn't choose any lower qualities because they all have the same penalty to quality itself. So what this means here, this is a legendary, so Q5, speed 2. We need 4 of those, legendary, speed 3, and we need 4 of those. So that means that in combination, we'd need 4 beacons to do this. And I think I've done that. Yep, correct. So same thing now in the recycler. The recycler, its most optimal is a speed 3 and efficiency 3. And the efficiency 3 is just a placeholder because the distribution effect of the beacon will effectively take, and let's talk about that directly in Factorio. So if I undo this and I show this here, I know that this is going to make a penalty of minus, or basically speed increase of 2.5x speed. And then that's being distributed. So the moment that I add this, this goes from right now, it's 585%. Let me take all the quality modules to make the math easier. So this is 625%. In theory, then you would say, okay, if I add another beacon, right, then it should be 2x that, or 1250. But it's not, it's 884. And that's because as you continue to add more beacons, the distribution effect, right, of that beacon will not be like basically the full power of 250%. It's going to slowly reach a point where it caps out all the way at like 20 beacons. And so this scale here is one of the reasons. So that was the fun part of this calculation here, was saying, hey, given all these possible combinations, what's your best throughput? Now, I'll give a disclaimer, and what was interesting to me too was that productivity at the very end, and I've kind of tested that in practice, but it wins just ever so slightly over straight quality. And it turns out, and I know we're talking like peanuts here, this is 0.1 per second on output. So, and actually you can continue to add more beacons. I've calculated it actually just for fun up to adding 7 different beacons, but that diminishing effect really starts to show its course because, and I'll just go ahead and just do this live because why not? Nothing ever goes wrong when you try something live. So if I change this down here and I wind up saying, hey, I want, let's see, the beacon count when I generate this, I'm going to generate it as up to 6 beacons here. Cool. So let's go ahead and run that simulation and save. Let's go ahead and run it. And there we go. So now we have a lot more simulations to run. So this is going to take a little bit. I'll go ahead and just wait for this brute force calculation to be done. All right, results are in. So if you remember before, we said there was 32 items per second that we were getting out with 4 beacons. Well, this might shock you, but oh, we're only getting 2 more-ish per second for a little bit more petroleum and water, but that's about the max cap that we're going to get. So, and the trade-off here is then we're also going to need a lot more modules around, and we're going to complicate the design space, make it less compact. There's a whole bunch of trade-offs. It's fine. These are cheap, making quality, like legendary stuff in like that late game where I'm at. But this is showing that convergence that I was talking about. So you can continue to add more beacons, right? But as your speed goes up, your quality goes down. So there is some theoretical maximum. And so it's really like we're converging towards the point of like 34, 35 as you continue to add speed beacons. So really the benefit that you're going to gain isn't all that much, right? So now the recycler, in order to deal with it, we're going to have less cryo output of common, but now the recycler is working about the same in terms of like how hard it has to work, but you're effectively just reaching a convergence point. So that's why I've chosen the specific combination of modules is to use just 4 beacons because it works out well in the design. So I could have chosen any of these options and they would have worked fine, but as long as they were over 30, because that's what I need for the actual science. And so I chose 32 and 4 beacons because it worked out well in my design, and also minimized the number of recyclers that I wound up needing. So anyway, that's the math. Back to design. Now that you know that with 1 cryogenic plant, you immediately look at this design and you would say, okay, well the math shows that, all right, you don't need 4. And you're right. This was the very first design that I came up with. This worked fine. This uses a silo chest, did not have the optimal amount of beacons, and ultimately in the end, this was just overkill for this because I'm producing twice the amount that I actually need. So this has already been scrapped. So I won't dive into that. I did start to get into some fun stuff here. So it turns out that cargo wagons are really, really good for this. Actually, even better than rocket silos. other than the fact that it's kind of annoying because now you're locked into a 2x2 grid rather than like being able to place it anywhere on the map. But that being said, the really nice reason, and the reason that these are good, is because of this. So let's go through this. So one of the nice things that comes up when you're working with like quality upcycling is that traditionally, and the way you've seen this on this silo here, is you're going to have an input and output, so 2 inserters for this. If I take this same concept here, right, and I could apply it here and put it on the cargo wagon, and that will work just fine too. But there's a funny thing that's kind of sneaky about this, and I alluded to it in my last video. But we can shove and put these inserters here underneath this cargo wagon. And just, again, just for like point of clarification, you put 2 down, you can kind of hover over this and hold shift, and eventually you'll get a cargo wagon to place over it. You can blueprint this, control shift, hold down, select trains, now you got a blueprint. That's what I've got. So that's what I just used. So anyway, so that being said, what you can do now is you can technically fit 2 under here. That's how I was trying it out with uncommon. But now what you can do is you can put this into here, and you can actually place this all the way up right there. So all of a sudden now you have a direct throughput that this is going to immediately shove it right back in. So whatever items you pull out, it's going to pull in. And you can also now place 4 like this all around it. So it's really convenient for this because now I've already, just through this here, I've removed 4 inserters. So really useful thing. I hate this for a lot of reasons for design purposes, because now I can't make anything symmetrical anymore. Because like most of the designs that I'm making rely on this 3x3 grid where I start putting, you know, things in this like 3 line here and then have things all nicely reflected on both sides. So I can't do it. So I don't have OCD, but the tendencies that I currently am feeling when I'm designing with cargo wagons is I know it's probably more optimal, and we'll test that here in a second, but it's cursed, and I kind of like that it's cursed, but I don't like that I can't make symmetrical designs with it. So in practice, the way that this works, and the way that this was designed, and I'll talk through this piece here, is I have a couple things going on, and we'll break this down. So first off, I have the cryogenic plant. I have a constant, and I don't have circuits hooked up to this, but because there's a tick delay, and the biggest thing that you're trying to deal with, and you're seeing this pink flashing light, because of this constant start-stop nature, and it happens quite a bit, of whenever there is any quality that's on the output there, it's only going to stack to 2 items. So you're going to need, and we'll slow it down just to watch it here, you're seeing the machines flick on and off like this whenever it happens to produce a quality item. And you really need to, in order to maximize the throughput and actually get the ratio that you want, adding a circuit here is going to delay it by 1 tick, and that adds up every single time it produces a quality item. So I'm not going to be making any circuit improvements that I've made before by limiting and throttling the inserters. So they're just going to rely on wakeless, and that's better. So, and the reason is because then this way it can constantly pick up the items as they come out and shove them then, you know, into this cargo wagon. So that's why these don't have circuits. This one here on the end, all it's doing here, and this doesn't even have to be in there, it's just acting like a filter. There's a couple different ways to do it, and I've changed it later, but the point is like, I just filter the quality items that I want, and that's basically it. Yes, I guess the other way to do this is you could use, to be fair, let me clear my inventory. You could use this, and you could say quality filter greater than uncommon, or greater than or equal to, and that'd be fine. However, later on, I wound up using this and I wound up changing the logic. Let me talk through that. I've already designed the blade, so I'm going to show the actual logic that's used here. So I only use this one inserter that's left over. So I'll just stick to now talking with this. Just when it happens to be greater than 15, and that only really happens, and I'm reading this, it's for the 1 tick, because this was a stopgap for these. These would stop for a brief moment whenever this would swing, and there is a very real chance that while this is swinging, and takes about 4 ticks, you know, to fully, you know, move over, that this would get stopped. And that stopping and starting was enough to actually slow down the throughput. And since we're so close to that 30 value that I talked about so much in the last section, that became an issue. So having this, and that's why I didn't use the other type of filter for this, was I wanted a specific condition to cover the edge case of reading here, what is it holding? What is the actual cryogenic plant outputting? And then finally, and I'm realizing I don't need this anymore. And then finally, just is the sulfur, like what I'm saying is, read the contents here. Does it currently have more than 16 items or more than 15 items? And if that happens, that's most likely this is about to swing. So click this on and just happen to grab some of the uncommon items out of there, or greater. So, and then this one's always grabbing blue because it'll happen more than not, and so forth. So always 2-to-1 ratio on the common versus uncommon, and that's basically it. So the other items that are in here, when I talked about this calculator before, so even though we're at a point here, and I'll just use, it doesn't matter, whichever one of these is an example, the inputs and outputs, right? So even though like all these recyclers are very close to being able to devoid all these, this is going to need like 3 passes to fully destroy that. And so you're going to start getting into a bottleneck scenario. So to account for that, what I did was I just added one extra beacon here, only, or not beacon, but recycler, only in the case where the contents of the rocket silo are greater than or equal to 50. That means at that point, these are completely full, in other words. The same thing happens over here for when this is deciding when this should turn on and off. I have the same concept here, but again, we're just using a cargo wagon. And so I'm reading now the contents of the recycler, and whenever the recyclers are greater than or equal to 180, because they can fully fill 100 of them, that's when it's going to go and swing and use this as just to quality upcycle a couple extra that these can't handle. And this can only handle 51 per second, but that's more than enough for this case, and that's why I'm just using speed 1s here. So, in essence, the whole design here and the placement of these is really critical. So we saw that the optimal amount was 4 speed 2s and 4 speed 3s. And you're seeing here, this is a fully designed stack that's here on the top, constantly running, producing 240 items per second. And this is fully backed up here. And I'm stacking them only just to limit the amount of swings that these stack inserters have to make. And it's just a UPS reason. You can easily just do this with like not having a stack belt, and it'd be more than enough throughput. So that's the reason I've chosen that. So that's covering a little bit of the sulfur and some of the shenanigans that you can do. So I've designed a couple different blades, and I'm going to go into those in a little bit more detail here now. So, but yeah, so I've gone through that, but I want to talk through, like, this has been a lot of different workings and designs through this that I've been trying to go through in different concepts. So I'll dive into the actual core designs of each one of these next. All right, so we have 4 different blades that we're going to talk through that we're also going to test. Each one has slight variations and differences. So I will ultimately go back and redesign one of them depending on which of the options turns out to be the most favorable. And then if there's one that's just a clear winner, then we'll just go with that one. But otherwise, I'll go back. These are modular. They're easy to take a piece because each of these are basically the exact same design philosophy. Fluids on the bottom, red circuits next, some form of sulfur processing. So either the cursed cargo wagon design, and I hate this because it can't be symmetrical, but I've just given in to the cursed nature of the cargo wagon and just made it look like a tumor. So this is fine. So then we've got here the same modules here. I would love for this to work, but ultimately the other one just might be better. So we'll go with that and see it afterwards. The test scenarios, the reason why I'm saying that the cargo wagon is better is because these add overhead for the spaceships up above the planet, so orbiting. So in the simulations, I'll add some ships, like 10 of them or something, just so that there is that interaction. So then after this is created, the difference is all the ones on the right here are using the same head module. I originally designed one that was used too many beacons, and talking on my Discord group, I was talking with one of the people on there, and we were going through, and she created a slightly better design here. So ultimately I wound up using hers, so thank you very much for her design contributions to that. The only things that are different about this design that I've added was just the clocking, and then otherwise it's basically remained untouched. So that is the head module for these. All three of these have the same one, because ultimately I like this better just because it is significantly more compact than this one. What is this one over here? I'm going to be testing out a fully directly inserted build. So this is a common design philosophy that people will tend to use, right? So minimizing the number of belts, but you're using a lot more buildings to do this. So turns out here we perfectly have enough buildings to supply everything that we're going to need to make this science, but this is a significantly amount of more buildings, but it allows for complete direct insertion and still keeping these, what was I going to say, the assembly machines making the science still having fully surrounded by 11 beacons. So that is going to be the core concept, and this is also clocked, of course, like all the other designs. So all of these are producing 240 per second without any stops or starts. So the way that this is going to work for head-to-head comparison-wise, these are exactly the same in terms of their base inputs, so we're just going to be testing then having less buildings and belts and pulling things off of that versus direct insertion. The next test then afterwards from this version to this version is we're going to be testing out here whether using, funny enough, basic oil processing is better than using advanced oil processing. And because in the late game where I'm at, because of mining productivity, oil is free effectively. So this is only, in theory, 4 buildings, whereas this one is a total of 7. So all of these are clocked though, so just to show that here. So these will turn on and off depending on when they're actually needed. This one, so you'll see here, I just have a circuit condition, and the way this works is an RS latch, and I do this for all the fluids. So now that we're in fluids, let's go and talk through that. So the way that this works is I monitor something that has a fluid content. You can do it directly in the buildings themselves. I just like to use a storage tank. So, and it makes it so it's easier for me to read this. So the way that this works, there's 2 of them, max capacity is 50,000 that they can put inside of them. And what this does is it just says, hey, whenever this is running, I want this to continue to run until we get to 45,000. I'm not doing quite 50 because the fluid throughput starts to diminish as you get to the max capacity of the entire, the pipe. So it makes sense in this case that I'll say like, okay, I'll cut it short, about 5K less. So, about 10% less than that, so that it has always max flow rate, and then it will get down to, once it, like in this case where it stops, I want it to wait now until eventually we get down to being below 25,000, and then we kick it on again. So that starts the cycle on and off. And that works just by this particular here. If you look at this cider combinator, it's just looped back on itself. It creates that check mark when the check mark gets created because of the condition, and then just is satisfied. Then it just runs the below state, and then otherwise on the top state. That's an RS latch. So that's what I'm using. So that way these are explicitly turning on and off all the time. And the reason I'm doing it is because they actually get so that the active state of those items actually goes and gets fully disabled, like right here. Otherwise, if you don't do this, these will continue to run no matter what, because it's constantly monitoring and checking that fluid is flowing. As long as fluid is flowing, they're going to constantly run, and so actually starting and stopping them has a benefit for UPS performance. Same for pumps, etc. So here, this concept works out as well, where this is making about 4,000, which is what we need. We need about 200K per minute, so these times 3 isn't quite enough, so you need 4 of them. And then over here, well, this one makes easily enough, but having just 1 is not enough to actually make the 200K a minute that I need. So I need to design that as well. So that's going to be the difference. So when I'm talking about these 2, and I'll turn off the debug menu again, we've talked about this is direct insertion. Here we're going to be feeding all the items and directly crafting them now and putting them onto belts. And then this design is a complete copy with the only difference being the fluid input, so we'll test that out. And then finally, this version versus this version is exactly the same, except it's using sulfur processing. So then again, this is on the bottom. So the way that the testing will work is, let's say there is a portion from this design that's better than this design. Or rather, if this design wins, I'm going to assume it's because the fluid processing on the bottom is better. If this design wins, then I'm going to assume this is better. But let's assume that the advanced oil processing is better for UPS in the tests. Then I'm going to say, okay, I'll take this design and I will compare it then, and I will basically copy that and put that back over here. And that's in the case that the cargo wagon here wins out over this one because they're both the same. So in each of these, I will just decide and test all the different combinations and then cross-analyze each of them. And whichever one wins, then I'll make a final version with a composite of all those different subcomponents. And then we'll see if there is any benefit or if there's just a clear winner. So with that being said, I'm going to get into benchmarks next. So I've set this up so that we are basically just mining directly here, and then all the inputs are going to be coming in here. I've set up 65 of these and copied them with Region Cloner, and then they're all going to be outputting, and then we're going to be creating for all of these different benchmarks around 930,000, 940,000 a minute. So on average. So I've added, the reason I'm talking about it is that I've added these additional just space platforms just so that there would be, I know that there is some interaction with rocket silos and having a ship above, so I'm kind of curious to add that to make it a fair comparison. So far I'm not noticing a huge difference with the rocket silos, but we'll see overall. Anyway, that's it. So I'm also going to add what I did to mention. I'm going to add the old science design, so the original, not that monstrosity, this one. I don't want to talk about this. This was a concept that I created. This was terrible. So yeah, we all start somewhere. Anyway, so this is the design. I'm going to use the old design in here, and we'll benchmark and see if the UPS is improved compared to that, and then all the other comparisons we've talked about. All right, so conclusions are in. I ran all the tests, and it turns out we just have a very decisive, clear winner. So I'll go ahead and reveal the sources. So it turns out that, very fascinatingly, the basic oil and sulfur wagon combo had a clear UPS improvement over everything else. So interestingly enough, so like we go through the order here, the chemical plant V1, and I'll make this a little bit bigger so that it's easier to read all this. This was the very first design. And instead of looking at the UPS numbers, I'll just say just basically the average UPS for was like just across the board, all those values were the best for the sulfur wagon shenanigans. So in here, was really interesting to me is just kind of looking at the percent differences here. So the original design that I had is not shown here. So like there was just doing the very first one where we did the direct insertion. That made like an 8.4% improvement. But then getting away from direct insertion and just having a minimal amount of buildings, it makes sense. Having more buildings in general or less buildings makes a big difference. So getting away from direct insertion and then just now having some belts with the clocking method, that doubled the performance over it, which was interesting to see. So then what was interesting though is going from the advanced oil, and the only difference was the basic oil versus this one with silo chesting, that gave already like a 3% increase, or over that even. So that was a fascinating discovery. So it makes sense that, okay, the basic oil processing recipe is just better overall. So I'll be using that for all future designs that involve chemical processing. And you can too if you have ludicrous mining productivity like I do and you just don't care about oil at all, or how much you're using of it. So then going from this, what was fascinating to me was that the Sulfur wagon had such a huge jump from this. Like it's over 5% going to the Sulfur wagons. So I'm happy that I simulated having the space platforms there, and I don't think you can credit the space platforms entirely. So when you include what I think is what's really going on is the fact that the inserters, and I'll actually go and hop over into Factoria to explain this. So I think the main reason why this works so well is the fact that, again, this is showing this concept here where these two items are sitting underneath the cargo wagon is where the inserters are. And because this can directly output, that means there's no limit anymore to it stuttering on and off, and the inserters having to constantly being woken up, grabbing items out of there. And just looking at this too, the wake lists they do turn on and turn off, but you wind up having a lot more of these inserters are effectively just running constantly. And that's okay because of just the minimal number of inserters that are in this. So it's interesting to me that this made such a difference. And again, this has all these extra space platform hubs up here, but this single method, and I think that's the biggest improvement that's coming from that. Here we are back on my lonely existence in Aquilo. So I've been waiting here, running the game as fast as I possibly can right now, and we are finally back at 4.4 million. So what did we change? So we're back at 100% on chemical science, and we have our new blade design incorporated. So I have the mod, just so people are aware of it. I use a zoom out mod, and I've just increased the zoom so we can watch the entirety of it in all its glory. FPS will probably drop looking at this whole thing, but why not observe the whole thing in its beautiful glory? So what you can see here is this has already shrunk quite a bit in size. This used to be all the way out to here. This is now significantly smaller. So, and that's thanks to eliminating all the additional chemical plants. This is now fully backed up. This is fully working here, and I'm very, very satisfied with this build. This is one of the cleanest blades that I've created so far, in my opinion, but I'm liking it. So one thing that is very interesting is the amount of crude oil we are now consuming compared to before, and it makes sense. We only really needed sustained 568,000 a minute, and well, now we're cycling on and off at an average of 2 million. So yeah, although it's not resource efficient, it is without a doubt UPS efficient. So it means that these pumps have to run still occasionally for a little bit longer, but they are anyway circuit limited here to only run when needed and turn on and turn off. So this is it. So it feeds all the way back, and we'll do a nice overview going all the way back here, seeing the blue science slowly coming back and feeding all the way back into the labs. So you've made it this far in the video. First off, thank you so much for watching. This is my ongoing series where I am going to be optimizing the blades in my mega base. And so we've done the first 3 basic sciences before you leave novice. So we've done red, green, blue, purple's next. So now that I've got the simulator that I've written, that's going to make these designs significantly easier to create in the future if we have more complicated things like Sulfur. I don't think it's going to be as useful until we get to Aquilo, because that's where I'm doing on-site upcycling of ice. But we'll see when we get there. The reason that I haven't included common sciences as a comparison is because I don't think it's going to be a conclusive test to do one versus the other. Because in my mind, and just intuitively, I'm thinking the ranking is going to be common science on novice, then common science on Vulcanus, but not including the logistics of sending it into the cargo hub. And then finally uncommon. Like, I think the builds themselves will be less optimal if you just compare them. But what I want to test is, let's go and get a full lab setup. And let's actually pump all that science in there. And basically, because the labs are going to have higher swing time on the inserters. And also I think the labs themselves wind up using more UPS depending on how fast the items are depleting. So I might be wrong with that. So we'll see. So if at the end of that, that's going to be my final of the first 4 sciences, is doing a check-in, seeing how we're doing with that. And then we'll do the same thing, but I'm going to continue to explore it for other planets. I think the other planets are going to always benefit from it because it's less materials, and then the cargo landing hub is going to always be a bottleneck for you. So that's kind of what's planned and coming up next. Other than that, I've got one other project that's in the works. I was talking with Michael Hendricks, and he, in his 1000X Science series, he's right now going through and using biters to absorb pollution. And he brought up a really interesting mechanic to me, that there's the ability for you to absorb pollution on a very fixed rate if you actually allow the biters to spawn from basically the spawners themselves and kill them on a fixed rate. So I've been doing some experiments with that, and I'll have a video eventually on that, but that's an interesting project that I'm looking at, is like, can we actually use that to control the pollution cloud? Because this save file is like 350 megabytes, so I would love it if we didn't have to have it this size for megabases in the future, just due to the enormity of the pollution cloud that is on Novice, right? So if we can shrink this down significantly by surrounding it completely with biters or biter spawners, that might be really interesting. So stick around, subscribe if you want to see that. Other than that, as always, all the links are in the video description below, including the blueprints and all of the code that you saw in this video, and then in general, just any of the results, and that's always going to be on the backlog. You can always go back there and look at and grab any of the blueprints from there. Other than that, thank you so much for watching. Talk to you later.